Alright, so in this video we will cover Chapter 8, and this video has to do with, or this chapter has to do with periodic properties. And so basically we'll talk about how the first periodic table was developed, and then we'll talk about some uses of it. So we'll write out electron configurations, we'll talk about how to predict atom size, things like this. I think you'll like this one, mainly because there's no math involved. So I think you'll like that. And the concepts are really not all that tough. It requires a little memorization, but not too tough. It's stuff that if you practice it, you won't have any trouble. Okay, so let's talk about how the first periodic table was developed. So it was first developed by Dmitry Mendeleev, and this is a photo of him. He was a Russian scientist, I believe. And he argued that element properties were periodic functions, and that was based on their atomic weights. So he came up with periodic law, and he said, when the elements are arranged in order of increasing atomic mass, okay, so that's an important point here, certain sets of properties reoccur periodically. Sorry about that. So, hence the term periodic table, right? So what he's saying is, if you arrange all of the elements, and at the time there weren't so many known elements, especially not as much as we have today, but if we arrange them by their atomic mass, you start to see properties that reoccur. So you start to see sets of properties that become predictable. Okay, and he said elements having similar physical and chemical properties fall within a column. And always remember that columns run this way. Okay, so these are columns in the periodic table. Okay, left to right we call rows, and up and down we call columns. If you have trouble remembering what's a column and what's a row, remember that columns hold things up. So like they hold up a building, for instance. So I think that's a good way to remember which is a column and which is a row. So just remember columns hold up the building. Okay. So we now know that element properties are periodic functions of their atomic numbers. Okay, so what's the difference between atomic mass and atomic numbers? Those both sound very similar, and they are actually, in fact, very similar. But remember, this has to do with the number of neutrons and protons. Specifically, actually, let's not say neutrons. That's because that can be variable. Let's say it's actually to do with the number of protons. Okay, remember, so when we talked about isotopes, we said that each element is defined by the number of protons it has, and so is their atomic number. Okay, so whereas he only had really information about mass at the time, okay, but he still used that information to come up with this. What we now say is that it's really a function of atomic number. So actually his periodic table was powerful enough that he was able to predict elements that hadn't been discovered yet. And this was based on their physical and chemical properties. Okay, so for instance, gallium. Okay, so the left column, this column, is what Mendeleev predicted, and then the other is what the actual properties turned out to be. Okay, so for instance, gallium. Okay, so he predicted the atomic mass to be about 68 AMU. He predicted to have a low melting point, a density around 5.9, and that it would form oxides with the formula X2O3, and that it would form a chloride of XCl3. So what is this saying? This is saying that it would have a positive 3 charge on it, basically is what he's saying there. Okay, and what did he actually predict, or what's the actual properties? So that's what he predicted. So what are the actual properties? Well, atomic mass, 69.72 AMU, and remember that's a weighted average or a weighted total of all of the isotopes. Okay, had a melting point of around 29.8, excuse me. So he said low, 29.8 is reasonably low. Density of 5.9. We know that it forms gallium oxide with the formula Ga2O3, and it forms the chloride GaCl3. Okay, so what you can see is from his predictions, or from what he discovered, he was actually very accurate. And to the right we have germanium. So he said it would be about 72 AMU. It would have a density of about 5.5 grams per centimeter cubed. It would have a formula for the oxide XO2. Okay, and then the formula for the chloride XCl4. So again, here he's saying it would probably have a charge or an oxidation state of about +4. So in reality, it has an atomic mass of 72.64, a density very close to what he said, 5.35. It indeed forms oxides with the formula GeO2, and then GeCl4 is how it forms its chloride. Okay, so from these two examples, it's obvious that Mendeleev really knew what was going on. So he was able to predict things with a very high amount of accuracy without that much information. Okay, so I guess if we can extrapolate from that, from what I'm about to show you in this chapter, you'll be able to predict things about elements you maybe don't even quite know the name of. Okay, so if I show you the trends, I show you the periodic trends and how to use the periodic table, hopefully you'll be able to predict things based on elements that you didn't know before. Okay, so hopefully we can get at least a little bit of that out of this chapter. Okay, so let's talk a little bit about the arrangement of the periodic table. So the elements are arranged from left to right in increasing atomic number. So remember, atomic number has the most to do with the number of protons. Okay, so they even outline that for you here, the number of protons. Okay, the rows in the periodic table are referred to as periods. So this is left to right. Okay, rows. Try to draw that a little neater. Oh, I can't draw an arrow today. Try this again. A little better. So these are rows. Okay, then columns within the periodic table are sometimes referred to as families. And this is a common way to refer to them because they have similar properties. And just remember, columns run up and down. Okay, so this is columns. Okay, and they're called families because they generally have similar physical and chemical properties. Okay, the elements, their names, and their symbols are given by the periodic table. Hopefully that's old hat by now. Okay, so the electron configuration. So this is the first thing we'll learn to do with the periodic table in terms of its arrangement. Okay, so according to the quantum mechanics, what we just studied, so the location of the electron around the atom's nucleus is described by 4 quantum numbers, and this is what we just went over. So N, remember that's our principal number, that's our energy level. L is the orbital type, so SPDF. M sub L is the orientation, so remember that's how when it's the actual orbital itself splits. And then M sub S, which is of course the spin, so remember that was +1/2 or -1/2. Okay, and we said that no 2 electrons can have the same 4 quantum numbers. And this again is the Pauli exclusion principle. Okay, so remember you have to obey Pauli or he's going to come get you. Okay. Well, based on that, we can also write electron configurations. And this is just a shorthand way of explaining where the electrons are in an atom. Okay, in other words, it's a way to convey exactly where the electrons lie within the orbitals of an atom. Okay, so for instance, if we look at helium, so helium, atomic number 2, so it just has 2 electrons and 2 protons. Okay, and it has the configuration 1s2. Okay, so within this small, piece of writing, there's a lot of information. So the 1 tells us the energy level, the value of N. Okay, the S tells us the orbital type, so that gives us our L. Okay, then 2 tells us the number of electrons inside of that orbital type. Okay, so we know that S, so the value of L here would be 0. So the M sub L is ± 0, in other words, just 0. Okay, so it only has 1 orbital, and we know each orbital can only hold 2 electrons, so the S orbital we know can only hold 2 electrons. So this is an example of a filled S orbital. So 1s2 is a filled S orbital, so it means it has It's on the energy level 1. It's S-type shape. And it's full because it has 2 electrons. Okay. So next we have the Aufbau principle. So this is the arrangement of electrons around the nucleus of the atom. So electrons are arranged around the atom's nucleus according to the Aufbau principle. Electrons enter the lowest energy level, in other words in, and orbitals available. Okay, so electrons will enter the lowest energy subshell that is empty in that energy level. So in other words, it won't go into, for instance, the p orbitals before it goes into the s orbitals. So you're going to fill your 1s2, then fill your 2s2, and then fill 2p. But you wouldn't fill 2p before 2s. Okay, so always fill from the lowest energy first, and that's Aufbau. So for example, this is basically what I just said. So for 2s, n is equal to 2, l is equal to 0. So n sub n plus l is 2 plus 0 is equal to 2. And then for 2p, we have n equal to 2, l equal to 1. Okay, so 2 plus 1 is 3. So we would fill, okay, the 2s before the 2p, since it has value of 2. This calculation isn't necessary if you understand, okay, if you understand how to arrange the orbitals. But if this helps you, then by all means. But if you just know that of course 2p is higher in energy than 2s, then you're good to go. Okay, so the electron goes in the 2s and not the 2p, just like we said. Okay, so this is a visual representation of the order of the orbitals. Okay, and this is a very, very good thing to know. Okay, I wouldn't necessarily expect you to recreate this exact picture, but you should know the exact order of these orbitals. So you should know 1s, then 2s, 2p, 3s, 3p, 4s, and it's pretty much in order until you get here. Okay, so notice that the 3d orbitals go before 4p. Okay, so you go 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, etc. Okay, so it kind of throws a little bit of a wrench in it, but that's because those are lower in energy compared to the 4p. And most of this you can find on your periodic table. So you go from hydrogen to helium, okay, that's your 1s, lithium to beryllium, that's your 2s, boron to neon, okay, that's your 2p, sodium to magnesium, 3s, aluminum to argon, 3d. Okay, then you go potassium to calcium, okay, that's your 4s, and then look what's next to there. Okay, so that's where our 3d starts. Okay, so then you put in your transition metals, and then you go to 4d, and then you go to 5s. So what I'm trying to say is the information is there for you. You just have to know how to read it. Okay, but make sure you know how to write this electron order, and we'll do some practice with this. Okay, so what was I trying to say before? Okay, so this is our S block. Okay, so everything in blue, that's our S block. Then this pink, sort of reddish color, this is our P block. The yellow is the D block, and then the green is the F block. So we have 1, S2, 2s2, 2p, 3s2, or 3s, 3p, 4s, 3d, okay, and then 4p. Okay, so that's how we arrange these. So the information is right there for you. Okay, so, but just remember, these are 3d. Is where we start here. We don't start from 4d, we start from 3d. And that just has to do with the energy of those actual orbitals themselves. Not so important for us to necessarily understand that just yet, but make sure that you know where they go. That's the important thing right now. Okay, and then remember that the lanthanides and the actinides actually go in there. Okay, so let's fill in some orbital diagrams. Okay, so this one is for lithium, and this is an example of it's called a box diagram. Okay, and the boxes just represent the actual orbitals themselves. Okay, so just the way that in the previous one we use sort of lines, sort of just dashes. Okay, this is the same thing, but here we use boxes. Okay, so it says lithium has an atomic number equal to 3. So to be neutral, it must have 3 electrons. Okay, so it has 3 protons, it has to have 3 electrons. Okay, its electron configuration is 1s2, 2s1. Okay, because it has 3 electrons. So how would we fill those into the boxes? Okay, so you're going to, of course, start with 1s, okay, your 1s orbital. And we have 2 electrons. So before we go on to 2s, we'll put 1, 2 into 1s. And you can start from spin up or spin down. It doesn't make any difference. Just purely aesthetic. Okay, but now we have, so that's 2 electrons, and now we have 1 more left over. So where does it need to go? Well, we would move on. So if we follow our periodic table, okay, so let's go back. So we filled in 1, 2. Okay, now we have 1 more. So where do we put it? Well, we have to go to the 3s. Okay, so we would go here. Or 2s, excuse me. Okay, so that's what we're going to do here too. So 1, 2, and the last one goes there. And it will just stay unpaired. Okay, so that's really it. So as long as you know the order, okay, then you know how to fill them in. Okay, now we have nitrogen. So atomic number 7. Okay, so it has 1s2, 2s2, 2p3. Okay, just based on, again, the periodic table. Just follow it like a map. Okay, but now we need to use our Hund's rule. Okay, remember Hund's rule tells us, if we go back, I didn't mention the Hund's rule yet, did I? Okay. Okay, well, Hund's rule is going to tell us that we need to place the electrons. Oh, it's down here below. So place the electrons in a set of orbitals having the same energy, or when placing them in electron. Or let me start over. So when placing electrons in a set of orbitals that having the same energy, and we call this being degenerate. Okay, it just means they have the same energy. So for instance, the 2p. Each of these 3 orbitals have the same energy level, so we call them degenerate orbitals. Okay, the electrons are placed singly as long as possible. So in other words, you want to singly occupy the orbitals before you double occupy them, and that is Hund's rule. Okay, so we start from, we have 7 to put in. So we'll start from 1s, then 2s. Okay, so now we have 3 left over, and we want to put them into the p orbital. So we put them singly placed first. Okay? So it should look like this. It shouldn't look like this. We shouldn't put in. This is not correct. Okay, so we shouldn't doubly fill one orbital and then put one just by itself. That's not how we're going to do it. We're going to put them like this. And generally you write them with the same spin. Okay, so that's for nitrogen. Okay, what about sodium? So now we have 11. Okay. So 1s2, 2s2, 2p6, 3s1. So this is a good place to point out that another way of writing electrical configuration is what we would call the noble gas notation. So for sodium, let's go back to a periodic table. Okay, so for sodium is right here. So what you do with noble gas configuration is you go back one. Okay, so here, and you find the closest noble gas that's behind it. It's never so you wouldn't want to go this way. You would want to go backward. Okay, so go to neon. Okay, so you just write neon in brackets and then finish out the electron configuration. Okay, so we're back to sodium. So we would write neon in brackets and then we'd say 3s1. Okay, so let's fill these in. First we fill our 1s, 1, 2. Okay, then we fill our 2s with 2. Now we're going to singly occupy the 2p. Okay, now we still have some left over, so we're going to fill in. We're going to give them, we call this a pair of electrons, so we pair them, we spin pair them. Okay, now we have one more, so we know that has to go in the 3s. We wouldn't put it up here in 3p, because that's going to be higher in energy. No, we're going to put it into the 3s. Okay. So hopefully that makes some sense. Do some practice writing electron configurations. I don't think you'll have any trouble with it. Just make sure you do practice it so it doesn't sneak up on you. Okay, so now we have inner core electrons versus valence electrons. So inner core electrons refer to the electrons that are in the filled shells. Okay, so for instance, 1s is almost always filled for every element aside from hydrogen, right? Or helium. Okay, so those are going to be our inner core. So it's the filled shells. The valence electrons are those electrons occupying the outer energy levels. Okay, and these are the ones that are on the outermost part of the atom. So, for instance, here they would be your 3p. Okay, so these 2 electrons in the 3p. Those would be our valence. And this is where everything happens. So the valence electrons are responsible for all the actual work. So they're responsible for the bonding, making cations. If they're removed, they make cations. If we gain them to our outer shells, then we get anions. So everything we talk about in terms of reactivity, in terms of bonding, forming ions, all this kind of stuff, we're talking about the valence electrons. The inner core ones, for the most part, they sort of establish the properties of the atom, but they don't really do a lot of work unless we start to pull off our valence. And once we start to pull off our valence, it gets harder and harder and harder and harder, okay, to remove them. But that's where essentially everything happens. Okay, so let's take a look at some of the more important blocks, or the important blocks of the periodic table. So one is everything you see in yellow. So this is your transition metals, sometimes just called the transition elements, mainly because they transition from sort of the main block metals over to our non-metals and metalloids. Okay, so we call them the transition metals or the transition elements. Generally speaking, we call them the transition metals. And this is where your d electrons are. So all your d electrons have to do with the ones in yellow. That's why we call it the d block. Most commonly, you'll hear it referred to as the d block, or transition metals too. Okay, so just remember your 3d electrons are actually in the 4th period and then down from there. But this is where all your d blocks electrons go, is in the yellow transition block area. Okay, then we have our inner transition metals. Okay, so the stuff in green, and we call them the inner transition metals because they go in this space right here. Okay, and there are reasons we pull these out. Mainly is that it throws off the trends within the periods if we don't remove them in this way. Okay, so they do have some effect on things like the size of gold and silver, for instance, are affected, or the trend for that is affected by these inner transition metals. Okay, but they sort of have their own unique properties, and that's why we pull them out. Okay, so this is where all your F block electrons go. Okay, so remember that they start in the 6th and 7th period. So once you get down here, you go lanthanide, and then here, 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 here. Okay, so just make sure you know where those go. And for most periodic tables have that marked. Okay, they don't keep it like a mystery or anything like that. Okay, so when we start to talk about electron configuration, there are a few cases where the actual electron configuration, specifically those found within the transition and intertransition metals, have an arrangement that's not predicted by the periodic table. And this is mainly because the energy level between the s and d orbitals is not that large. And what this means is you can have some balancing or some pairing between the s and d orbitals that actually becomes more energetically favored. So in other words, it might be lower in energy to move an electron from the s orbital into the d orbitals. Okay. And there's only a handful of these cases, but it does happen. And it's not always the easiest thing to predict. So I've given you some examples here. Okay, so these are the ones I would expect you to know for sure. So I could ask you any one of these, and I could say, predict the predicted and actual electron configuration of ruthenium, for instance, something like that. Okay. So if we take a look at copper, so I have this one highlighted, so let's talk about that one. Okay, so its electron configuration will be argon, and then 4s2, 3d9. So this is predicted by our Aufbau. So remember, fill in your lowest energy first, and then start to fill in the next, so singly occupy the next orbital up in energy, okay, then start to doubly occupy until you run out of electrons. So you would predict it to be 3d9. But what actually happens is that you end up with 3d10. So energetically, it's better to fill or completely fill the 3d orbitals with 2 electrons, in other words, to pair them. So you end up with all 5 orbitals filled with paired electrons, than it is to keep that same, to keep this electron over here. So instead of having this, you would have this. So this is less stable than it is if we put it over here into the D shell. So notice these should be higher than 4s, but they actually go down in energy a bit, and that's why this occurs. Okay, so if we go down in energy, it becomes more stable. Okay, so it's better for the atom to be arranged this way. So your actual electron configuration would be 3d10 4s. So actually, they become lowered in energy. Okay, but we would still write 4s1 3d10, so we don't actually write it this way. Okay, we would still write 4s1 3d10, and notice that's consistent throughout, even when we have a 0 occupied, and so an unoccupied s orbital. We still write them in the correct order, okay? Because this is not, knowing if it really is down or up in energy is not something you can easily predict with something just like electron configuration. You need to do some computations for that. So we still write them in the correct order. Okay, but notice this happens, so 5s1 4d5. So it's more, like with this one, it's more energetically favored to have all singularly occupied orbitals instead of having one paired orbital. And you can kind of look at these on your own. For instance, with palladium, it's more energetically favored to have a completely filled d orbital. Okay? And but that's mainly because it's better to have 5 orbitals lower in energy and give up some of that 5s energy. Okay, so just make sure you know these, and you can predict them and also know their actual electron configuration. Okay, so here we're talking about the full shell look. In other words, we say in quantum mechanics that an atom with 8 valence electrons should be unreactive. That is, it should be very stable. And that's why we call the Nobel gases the Nobel gases. So these have 8 valence electrons, and therefore they are very stable and unreactive, aside from helium, okay, which only has 2 electrons, but still it's very stable. Okay, so the full shell look implies stability compared to elements having either 1 alkali metals or 1 fewer halogens. Electrons should be predicted to be very reactive. Okay, so in other words, our alkali metals and our halogens are very reactive since they're only 1 electron away from having that full shell look. So they want to either lose 1 or gain 1 to get that full shell. So halogens have 7 valence electrons, and these are generally the most reactive nonmetals. So they'd rather gain 1 electron to form anions, and now they have a full shell. Alkali metals, with 1 more electron than a noble gas, are also very reactive. So they lose 1 electron to become cations. Okay, so electrons are removed or added in the valence. Remember I said the valence is where everything happens. So the valence shell, again, is the outermost energy level that contains electrons. And the valence, the electrons in the valence shell are referred to as the valence electrons. We said that already. Okay. So we have cations. So metals tend to form cations. Okay, that is, they tend to lose electrons, okay, rather than gaining. So cations is just the name for a positively charged ion. Okay, so if a metal, and generally it is the metals that give up electrons to form positively charged ions called cations. Anions, these are generally formed from nonmetals. Okay, and this means that we gain an electron to form a negatively charged atom, and that's referred to as an anion. So just make sure you know where this is happening, and of course it's happening in the valence. Okay, understand that cations are positive because we've lost an electron, anions are negative because we've gained. Okay, so let's look at the formation of some anions, or cations, I should say. Okay, so S-column metals, okay, so that's 1A and 2A, so your alkali and your alkaline earth metals, lose their S valence electrons. Okay, so for instance, magnesium goes from 3s2, okay, and it loses those 2 electrons from 3s to become the same electron configuration as neon. So it goes from being neon 3s2 to just being neon. But it also now gains a +2 charge. Okay, so notice we lost our outermost electrons in our valence first. And this is always what happens. So, for instance, 10 goes from 5p2, okay, and it can lose those 5p electrons, okay, to become 2+, or it can lose, so it can lose these first 5p2, then 5s2, they become +4. So notice, depending on how many electrons we lose, depends on what charge, or the charge we gain depends on how many electrons we lose. And down here we make a note that our d electrons are very stable, especially if it's a full shell, and they are essentially pseudo full shells or pseudo inner shells. So it's very difficult to remove d electrons. Okay, so d block elements lose their s valence electrons first. Okay, so we go from something like iron, where we have 3d10, 4s2, and it's going to lose those 4s2 before the d electrons. Okay, and then once we lose our s electrons, then we start to lose d electrons. Okay, and also we know that half-filled d subshells are also very stable. Okay, so f group elements lose their s valence first, and then their f valence. Okay, so very similar to our d block, where the f block also loses s first, and then f block. Okay, so just remember, for d and f block, you lose the s orbital first, and then you start to take away from the d and f block. So anions do the opposite. So anions gain electrons. They become negatively charged. So those electrons are gained in the valence orbitals, that is to say, the outermost orbitals. So oxygen goes from having helium 2s2 to p4. It will gain 2 electrons to become more like neon. So helium 2s2 to p6, which is the same electron configuration as neon. Okay, now it has a -2 charge. So similar for iodine, which is one of our halogens. Okay, so it's going to gain an electron in its p orbital to become 1 negative, or in other words, exactly the same as xenon. We touched on this in the last chapter, but just remember, if an electron configuration results in having unpaired electrons, we call this paramagnetism, and it's therefore attracted to a magnetic field. Okay, so these would be magnetic. Remember, I showed you oxygen can have that situation where it has 2 unpaired electrons, which makes it cling to a magnetic field. If it has all paired electrons, okay, so all paired electrons, this is diamagnetism. So that means it's actually slightly repelled or not attracted to a magnetic field. So unpaired electrons, attracted to a magnetic field. Paired electrons, slightly repelled or just not attracted to a magnetic field. Okay, so paramagnetism, attracted to a magnetic field. Diamagnetism is slightly repelled or not attracted to a magnet. So for instance, why is iron 3 oxide magnetic? So its ions, when with unpaired electrons, are paramagnetic, we say. And we say ions without unpaired electrons are diamagnetic. So if we take a look at iron oxide here, so F3+ in iron oxide has 5 unpaired electrons. Okay, so we have 1, 2, 3, 4, 5. So 3+ will lose 1, 2, and then 1 from our D shell. So we end up with 5 unpaired electrons. If we have unpaired electrons in this way, we'll be attracted to a magnet, so therefore we'll be paramagnetic. So that's all there is to it. Just knowing that if you have unpaired electrons, you are more likely to be paramagnetic than diamagnetic. If you have more paired electrons than unpaired, you're going to be diamagnetic. Okay, so hopefully you've seen so far, and we'll dig in deeper into this, but hopefully you've seen so far that the number of valence electrons has a big impact on the chemical and physical properties of the atom. Okay, the number of valence electrons follows a periodic pattern, and the properties of the elements should therefore also be periodic. Okay, and I think we'll stop this video here. I know it's only about 30 minutes so far, but we'll come back with a part 2, and we'll start going over our trends, and we'll finish the chapter that way. We're about halfway through, so I think this is a good place to break, and when we come back, we'll go over some of the periodic properties.